In the middle of the ocean, the captain gives the order to raise the sails. The wind is blowing directly toward the ship, and anyone watching would assume that the vessel is about to stop. It seems obvious that the wind will either hold the ship in place or slowly push it backward. But then something happens that confused people for centuries. The enormous sailing ship begins to accelerate and continues moving almost toward the direction the wind is coming from. At first glance, it looks like an impossible trick. If the force of the wind is moving in one direction, where does the force come from that moves the ship in the opposite direction? Did sailors really discover a way to cheat the laws of physics? Or have most of us misunderstood how sails work from the very beginning? And the deeper you look into this question, the stranger the answer becomes. It turns out that sails work in a completely different way from what most people imagine. The real secret is not hidden inside the wind itself. It comes from a physical effect that nearly everyone has seen hundreds of times, but almost nobody has noticed. Today, we are going to discover how a sailing ship can move against the wind, and why this same principle is still used in modern aircraft and advanced engineering. Imagine holding a wide shovel outside the window of a speeding car. The rushing air would immediately tear it out of your hands with enormous force. It seems perfectly logical that a sail should work the same way. A sail should catch the wind like a giant, powerful bag and simply absorb the direct force of the air. But this simple idea hides a major misunderstanding. For centuries, that misunderstanding kept sailors limited to the direction of the wind. If you place a flat wall directly against moving air, the force pushes only in the direction of the airflow. The ship can travel only where the wind is blowing, and not even a few degrees to the left or right. Then shipbuilders made a discovery that changed everything. They stopped thinking of a sail as a giant trap for catching air. Instead, they began shaping it into a curved aerodynamic surface. Imagine the wing of a passenger airplane, except turned vertically. When moving air reaches this curved surface, the airflow divides. One part travels along the inner, flatter side of the sail. The other part is forced to move around the outer, more curved surface. And that difference creates something far more powerful than a simple push. For thousands of years, ancient Egyptians and Romans used huge rectangular sails. Their ships could travel with the wind. But when the wind blew directly toward them, they had only two choices. They either dropped anchor or relied on heavy oars. Then, during the 6th century, Arab navigators introduced a revolutionary.
This underwater structure is called a keel. On smaller sailing vessels, a similar structure is known as a centerboard. Imagine a strong, flat blade extending deep below the bottom of the ship. It may appear simple, but it performs one of the most important jobs on the entire vessel. Water is nearly 800 times denser than air. So when the sideways force of the wind tries to push the ship to the right or left, the underwater keel presses firmly against the dense mass of water. That resistance creates an effect almost like a locked wedge. The enormous wall of water prevents the ship from sliding sideways. Once the sideways movement is blocked, the combined force has only one useful direction left. It begins pushing the ship forward along the length of its hull. The effect is surprisingly similar to squeezing a wet watermelon seed between your fingers. Press the seed from both sides, and it suddenly shoots forward. The sail creates the sideways force. The keel prevents sideways movement. Together, they transform the wind's energy into forward motion. But building a deep keel was not always possible. During the 15th century, Dutch merchants faced this exact problem with their flat-bottom trading ships. Their home ports were surrounded by shallow water. If they built deep keels, their ships would run aground before reaching the harbor. Without deep keels, however, their vessels were repeatedly pushed sideways whenever they attempted to sail against the wind. The solution was remarkably clever. Dutch engineers developed enormous wooden blades called lee boards. These large boards were attached to the sides of the ship. When the vessel needed to sail against the wind, sailors lowered the board on the appropriate side into the water. The board acted like a temporary underwater wing.
In 1590, the Dutch fleet used these side-mounted blades to perform difficult maneuvers in the North Sea during powerful headwinds. Their ships were able to move more efficiently than many larger and heavier competitors. The problem of sideways drift had finally been brought under control. But the engineers did not have long to celebrate. As sailing ships became faster, the air...
Even with a perfectly shaped sail, a ship cannot move directly toward the wind. At a very sharp angle, the smooth airflow begins separating from the surface. The organized movement of air breaks apart and turns into chaotic turbulence. Once that happens, much of the useful aerodynamic force disappears. The ship loses power and slows down. A single sail may look perfect, but it still cannot bring the ship closer than roughly 50 degrees to the direction of the wind. Try pointing the vessel closer, and the airflow begins breaking away. The sail loses its aerodynamic grip. The ship becomes almost powerless. Engineers needed another solution. Instead of making the mainsail larger, they placed a smaller sail in front of it. The large primary sail is called the mainsail. The smaller forward sail is called a jib. Between the two sails, engineers created a narrow and carefully controlled gap. And inside that small opening, something extremely important happens. As the wind...
Watch the mast of a sailing ship while it moves close to the wind. The tall structure bends into a visible curve. It may creak under loads equal to many tons. At that moment, the entire vessel behaves like a giant mechanical press. The ship is almost trying to tear itself apart. When sailing at a sharp angle to the wind, two enormous forces act in different directions. The sail pulls the upper section of the mast sideways and upward. At the same time, the heavy keel holds the lower structure firmly inside the water. This creates tremendous bending and twisting forces. The mast acts like a giant lever. It continuously attempts to pull its own mounting point away from the deck. The supporting cables, stays, and rigging stretch under extreme tension. They become like enormous strings ready to snap if even a small weakness appears. And if one part of the system fails, the result can be immediate. The forces transfer suddenly to the remaining components. A broken cable can overload another support. The mast may split or collapse. Its broken sections, still connected by heavy steel rigging, can become giant battering rams. They may crash into the deck or strike the side of the vessel. During the 1998 Sydney to Hobart yacht race, competitors encountered an unexpected and extremely powerful storm. Winds reached approximately 45 knots. Massive waves repeatedly slammed into the yachts. The combined impact of the water and the extreme tension inside... Imagine a sailing vessel that does not move through the water. Instead, it rises above the surface and flies across the ocean. It travels at speeds approaching 80 kilometers per hour while moving against powerful winds. It sounds like an extreme amusement ride, but this is the highest level of modern sailing technology. To reduce water resistance, advanced racing yachts use hydrofoils. These are underwater wings built from extremely strong carbon fiber materials. As the ship accelerates, water flows around the hydrofoils. The shape of the underwater wings creates a pressure difference. That difference produces lift. At first, the hull remains in the water. But as the speed increases, the lifting force becomes stronger. Then the vessel reaches a critical point. The entire multi-ton hull rises out of the ocean. The ship begins flying above the surface. Only the narrow hydrofoils remain in the water. Most of the hull's friction disappears. Water resistance can be reduced by an extraordinary amount. The vessel no longer behaves like a traditional ship. It becomes something closer to a flying machine. And then another strange effect begins. As the yacht moves faster, it creates its own apparent wind. The faster the vessel travels, the stronger the airflow appears from the crew's perspective.
That stronger airflow produces more aerodynamic force. More force increases the speed. The increasing speed creates even more apparent wind. The system begins feeding energy back into itself. The ship can...
At first, the idea seems impossible. If a sailing ship is already moving against the wind, then increasing its speed should make the wind harder to overcome. But something completely unexpected happens. The faster the ship moves, the stronger the wind appears to become. This is known as apparent wind. Imagine standing still on a calm day. You may feel almost no air moving around you. But the moment you begin riding a bicycle, wind suddenly rushes against your face. The air did not suddenly become stronger. Your movement created the sensation of a powerful headwind. The same thing happens to a sailing vessel. As the ship moves forward, its speed combines with the natural movement of the air. The result is a new airflow that can be much stronger than the real wind. And this changes everything. A fast sailing yacht does not depend only on the wind blowing across the ocean. It also creates a large part of its own airflow. The faster it travels, the more powerful the apparent wind becomes. That stronger airflow produces more aerodynamic force on the sails. More force increases the ship's speed. Then the increased speed creates even more apparent wind. The process begins feeding energy back into itself. But there is a limit. If the sails are not adjusted at exactly the right moment, the growing force can become dangerous. The ship may accelerate so quickly that the aerodynamic balance begins to collapse. This is why modern racing yachts use advanced sensors and computer systems. They constantly measure wind speed, direction. For more than a century, the shipping industry believed that engines had replaced sails forever. Steam engines became more powerful. Diesel engines made cargo ships faster and more predictable. Traditional sails slowly disappeared from commercial routes. It seemed that the age of wind-powered transportation had ended. But now the wind is returning. And this time it is coming back with computers, automated systems, and advanced aerodynamic technology. Modern cargo ships consume enormous amounts of fuel. Some of the largest vessels travel thousands of kilometers without stopping. Their engines must move millions of tons of steel, cargo, fuel, and equipment. Even a small reduction in fuel consumption can save enormous amounts of energy. That is why engineers began looking toward an ancient source of power, the wind. But modern cargo ships cannot depend on fabric sails alone. Their routes must remain reliable. Their schedules must be predictable. Their systems must operate safely in changing weather. So engineers developed automated wind-assisted technology. Rotor sails became one of the most promising solutions. These enormous rotating cylinders can be installed directly on the deck. They require no traditional ropes. They do not need large crews to raise or lower them. When the wind reaches the ship from a useful direction, the cylinders begin spinning. The Magnus effect generates a powerful sideways force. The ship's hull and rudder transform part of that force into forward movement. The main engines no longer need to provide all the power. They can reduce their output. And that means less fuel is burned. But the most surprising part is that the wind does not need to come from directly behind. Rotor sails can generate useful force when the wind approaches from the side. Imagine looking across the ocean and seeing a cargo ship covered with enormous vertical wings. There are no giant sheets of fabric. There are no sailors climbing masts. Instead, tall mechanical structures silently rotate toward the wind. The ship appears to belong to the future, but the idea is based on physics that has existed for centuries. Modern wing sails are designed to behave like aircraft wings. Their surfaces are rigid. Their shape can be adjusted. Some systems use multiple sections that move independently. This allows the structure to change its aerodynamic profile. When the wind direction changes, the wings rotate. When the wind becomes stronger, the system can reduce the angle. When conditions become dangerous,
the wings can move into a safer position. The entire process may happen automatically. Sensors measure the airflow around the ship. Computers calculate the best configuration. Actuators adjust the wings with remarkable precision. The vessel constantly searches for the most efficient angle. But there is a hidden challenge. The larger the wing becomes, the more powerful the aerodynamic force. At the same time, the force creates greater stress on the ship. The deck must support enormous loads. The hull must remain stable. The vessel must resist powerful rolling movements. A wing that saves fuel can also create dangerous forces if it is poorly controlled. Engineers must balance efficiency against stability. The design cannot focus only on speed. It must also survive storms, heavy waves, and sudden changes in wind direction.
Water is one of the greatest obstacles facing every ship. A vessel may have powerful engines. It may use advanced wings. It may generate enormous aerodynamic force. But the hull must still push through a dense and heavy fluid. That resistance consumes energy every second. The faster the ship moves, the more difficult the struggle becomes. At high speeds, water resistance increases dramatically. The hull creates waves. Turbulence forms behind the vessel. Friction develops across the entire surface. A large amount of energy is lost simply moving water out of the way. For centuries, shipbuilders tried to solve this problem by changing hull shapes. They made vessels longer. They made them narrower. They reduced unnecessary surface area. Every improvement helped, but the water remained a powerful barrier. Then engineers discovered a more radical solution. Instead of designing a better hull, why not lift the hull out of the water? That idea led to the development of hydrofoils. At low speed, a hydrofoil vessel behaves like an ordinary ship. The hull rests in the water. The underwater wings remain hidden beneath the surface. But as speed increases, water flows rapidly around the foils. The shape of the wings creates lift. The lifting force grows stronger. Eventually, the vessel reaches a critical speed. The hull begins rising. The water releases its grip. Within seconds, the entire ship can lift above the surface. For centuries, people believed that a sailing ship could never travel faster than the wind. The idea seemed obvious. If the wind provides the energy, how could the ship move faster than the source pushing it? But the answer depends on how the sail uses the wind. A traditional square sail mostly receives a direct push. Its speed is strongly limited by the movement of the air behind it. But a modern aerodynamic sail works differently. It creates lift. The force does not point directly in the direction of the wind. The sail redirects the airflow. The keel or hydrofoil redirects the resulting force. Together, they create forward acceleration. As the vessel gains speed, apparent wind becomes stronger. The ship begins generating more aerodynamic force. This allows it to move faster than the natural wind. The idea sounds impossible, but the physics is completely real. Imagine a wind blowing across the ocean at 30 kilometers per hour. A high-performance sailing yacht may eventually travel at 60, 80, or even more than 100 kilometers per hour. The ship is moving several times faster than the wind itself. It is not creating energy from nothing. It is using the wind from a different direction. The vessel's movement changes the airflow it experiences. The faster it travels, the more useful the apparent wind can become. The sail behaves like a wing. For thousands of years, sailors looked at the wind as both a source of power and an unstoppable obstacle. When the wind blew from behind, ships moved forward. But when it came from directly ahead, the ocean seemed to become an impossible barrier. Then, humanity discovered something remarkable. The wind did not need to push a ship from behind to make it move. It only needed to be redirected. A curved sail transformed moving air into aerodynamic lift. The keel prevented the ship from sliding sideways, and together, these forces created forward motion. What looked like magic was actually physics working in perfect balance. But the story did not end with wooden ships and fabric sails. Engineers developed rigid wing sails,
rotating Flettner rotors, and advanced hydrofoils. Modern racing yachts now rise above the water and travel faster than the wind that powers them. And giant cargo ships are once again turning to the same natural force that powered ancient civilizations. The technology changed, the materials changed, but the fundamental principle remained the same. The wind was never the enemy. It was simply energy waiting to be understood. A sailing ship does not break the laws of physics. It uses those laws in a direction that most people never expect. And perhaps that is the most surprising part. The force that appears to be stopping the ship can become the very force that drives it forward. Sometimes the answer is not to fight against the obstacle. Sometimes the